Yes, sir.
Today is February 23, no, 2022. Now, we have one more topic left. Okay. So, we may need to finish it in one or two meetings. No? And then, can we have our exam on March 7, everyone? So that I can give your grades on March 14. Is that okay?
Yes, sir.
Kasi pwede na daw eh. No? Pwede na sa second week of March mag-submit ng grades because the final especially for you because you are fourth year. And then the final exam is from March 21 to 26. Okay? I'll just give you pointers and sample problems and you can solve the problems in over the weekend. Is that all right? No? Over the weekend lang. So it's like a take home done at home. Okay? You follow?
Yes, sir.
No? So, ano saan ba yung aking I was looking at our text because we had an issue regarding the use of the tag in I have read samples, no? And then I look at the description of associative mapping. Okay? Associative mapping in our book. Do you follow? Any questions? So ganito yan, no? Associative mapping overcomes the disadvantage of direct mapping by permitting each main memory block to be loaded into any line of cache. So which means that it looks for the next vacant one. No? In this case, the cache control logic interprets memory addresses simply as a tag and a word field. Do you follow? Okay. The word field is actually the offset within the cache. You look at that, okay? Okay, sino ba yung may tanong last meeting? Dabon?
Yes, sir.
So,
Yes, sir.
So it's just a mixture of terms, no? The tag field here is actually the whole block address. Okay, the word field is the offset within the cache. Take note, no? It's specified that previously our tag field composes of a tag and a cache address, right? In the direct map. Okay, the tag and the cache address actually points to the whole block in memory. Okay, this time the tag points to the whole block in memory. So interchangeably, we can say tag or block when we say associative mapping. Okay, Dabon, is that clear?
Yes,
okay.
sir.
So pag sinabi natin, actually I was wrong in saying the tag field is not used, but the tag field is used to store the whole block address. Do you follow? Kasi dito sa ating in our demonstration of cache, at saan ba yung ating cache trace? Anyway, it's in our it's in our Dagger site, no? In the associative map, this is also called the tag. Do you follow? Ang tawag dito tag. Okay? The whole tag address is now used to occupy both the previous tag and the cache address, no? Do you follow? Okay, interchangeably when we say tag in associative mapping, we mean the whole address of the block. And when we say offset, this is the word inside the cache, no? Okay. Okay. Do you follow? I'll upload this again. Kasi it's very clear, no? Anyway, it's clear in our text. Nasaan ba yung aking text? Okay. Ito. No, it's not this. Wala yung aking Ito, no? So this is the associative map. The whole tag is used to store the previous tag and cache address. So the whole tag actually is occupied by the whole block address, regardless of whether it's inside the cache or inside the memory. No? Do you follow? And the word is the offset within the cache. Okay? Okay? Now in the set associative map, the same thing follows, but we just recompute, no, okay, we just recompute the address of the set to which the block belongs, no. So how do we compute the set? It's the block number mod the number of sets. Okay, that's where the block should be placed. Like in this case, we have 4 sets. Okay, so the block address mod 4, that's where the block address, or this is also called tag. Okay. Okay. So any questions so far? So can we move on now? So last meeting, we discussed, what did we discuss? Memory interleaving. It's actually a process of addressing memory across memory banks inside hardware. No? Do you follow? Because we know that TDR and SDR are organized into memory banks. Now, in a non-interleaved memory, the addresses are sequential inside each bank. 0, 1, 2, 3, 1, 0, 2, 4. Followed, the next address will follow in the next bank sequentially, and the next bank sequentially. No? This has a disadvantage in the sense that only one memory bank is active at the time. Do you follow? Do you follow? When in fact, no, these memory banks are physically different. Okay, they're physically separate, which means that when one memory bank is active, the others are not doing anything. Do you follow? They're just waiting until the address that is being asked will belong to them. Do you follow? So only one of the disadvantage with no interleaving is only one memory bank is active at a time. To illustrate this differently, no? We can have two-way interleaving in which we will have two physical memory banks. And the address is we skip from one memory bank to another. Okay? Do you follow? So address 0 is here, but the next address 1 is in the neighboring bank. Address 2 is on the left, address 3 is in the right, address 4 is on the left, address 5 is on the right, and so on and so forth. So that the last address will be on the left is 4094, on the right is 4095. Do you follow? The advantage with this is during the fetch of the first memory bank, no, the first half, no, the execution, or rather the instruction cycle, during the fetch of the first memory address, the second memory bank will wait. Okay, but during the execution of this, no, the memory chip address 2 or chip 2 will load memory address 1, which is actually sequentially the next, no, into the memory pipeline in the processor's pipeline. So there's a pipeline, which means that each memory chip has a pipeline, which means this belongs to pipeline 0, this belongs to pipeline 1. So that the next time that the CPU will fetch an address, or rather the cache will address a cache, will fetch an address in memory or from memory, it will not have to look for it in the actual memory, but only in the pipeline because it's already there. Do you follow? So when memory 1 is being fetched and then later executed, during the execution, memory 2 is now also being fetched. It can be done because these are two separate hardware circuits. Magkaiba sila. They can do things simultaneously together. Unlike in a no interleaving, no, while memory chip 1 is active, chip 2, 3, and 4 will have to wait. Okay? In here, when memory chip 1 is doing something, memory chip 2 can also do an advanced fetch. Do you get my point? No? Okay? So we interleave the address. Now, nowadays, no, you can have 8-way interleaving in most common DDRs. Okay? Ito, no? This is a 4-way interleaved. Ito, kung apat silang banks, like in this case, there are 1, 2, 3, 4, 5, 6, 7, 8. 8 banks. There are 8. It's an 8-way interleaved memory address. Do you follow? Okay. If there are 8-way interleaved, which means that there are 8 bytes being read at the time. Okay. Being read or written at a time. No? Which means that while the first byte is being read, all the rest are also copying or getting their values from memory. Okay, because there are 8 different banks which can do simultaneous reading and writing. Okay, so in this example, we have a 4-way interleaving where the first address is in memory bank 1, which is 0. Address 1 is in chip 2. Address 2 is in chip 3. Address 3 is in chip 4. So which means that when memory 1 is being executed, or half the phase of the memory cycle of memory chip 1, all the other 4 can now advance the read. Okay, so that there are 4 bytes that are being read in advance. So the next time around, when there's an address of 4, it's going to be placed on the next vacant space in the pipeline, so that when the next address is done, the CPU does, or rather is requested. No, the CPU doesn't have to go fetch it directly from memory, which will be very fast. Okay. Any questions so far? So ganun lang yung memory interleaving, no? Okay. I'll try to look for exercises on this, no? But wala yata ito sa libro. There's only a special appendix regarding memory interleaving in the book. Okay. Any questions so far? No. So now is a memory, no? Internal memory. Okay. So what are the types of memory that we know? We have RAM, the most popular one. It's called RAM, Random Access Memory. Do you follow? Alam na natin ito, di ba? It's read-write memory, which means that you can read and write. It's erasure. It's electrically byte level. Okay, addressed by byte, and the mechanism is electrical because some of them are magnetic. No? Volatile, which means that without power, okay, the RAM will lose its contents. Okay, well, it needs power in order to store the values properly. You know? The second is the read-only memory, or ROM. You know? Where do we find the ROM? We have a CD-ROM, right? You know? Aside from that, we also have a ROM in the computer, in the CMOS ROM. Diba? Where, do you know what the CMOS is? Ano ibig sabihin ng CMOS? Metal oxide semiconductor. No? Which means it's made of something, ano? CMOS, complementary metal oxide semiconductor. Okay, do you follow? In other words, it's a non-volatile type of memory. No, it's semiconductor, which means that it's made of transistors. No, but it's non-volatile, which means that it's hardwired. By the way, no, the contents are hardwired. You can buy a programmable ROM, which means that initially it's empty, and then you write once and then never erase again. No, you can only write once and never erase again. Okay, that's called a read-only memory. So the contents of the read-only memory are factory set, which means that when they come out of memory, or rather the factory, they already have values. No? What are these? Like the BIOS, basic input and output system. This is the part. This is a microprogram. This is a program that boots your operating system. Do you follow? Okay, gets the memory, the operating system running. No, meron siyang boot system doon, no? Okay, the programmable ROM or PROM is like a ROM that can be erased, that can be programmed, no? Erasable PROM is a PROM that can be erased several times only, not all the times, no? Do you follow? For a limited number of times, you can erase it and write it, erase it and write it. No? Electrically erasable PROM. The meaning of this is you don't need a factory equipment, no, to erase the ROM. You can erase it, no. You can erase it and set it again using your computer. A flash memory is actually an electrically erasable ROM initially, no. It's made of semiconductors, no? So a PROM, okay, a ROM erasure is not possible, no. Even a PROM, no, erasure is not possible, no. In an erasable PROM, Now, an example of this is a CD-ROM which can be rewritten several times, right? Diba merong ibang erasable CD-ROM, we can reformat it again. Not all the CD-ROMs, no? You can erase it by using UV light, no? Chip level, by erasing the charges that are on the CD-ROM, no? Okay. Okay. Now, flash memory and electrically erasable ROM are done electrically and now can be done, no, by ordinary computers, no? The right mechanism is electrical. This is electrical. This is masking, no? This is a process using a EEPROM programmer. Okay, a programmable ROM programmer. It's a circuit, no, where you place the ROM and then save the value there, no? Sequentially, no? So it's ROMs are non-volatile, which means that even without electrical power, they will store their memory. This misname at all, no? Semiconductor memory, no? RAM. Okay. RAM. Random access, read write is volatile. Why is this misnamed? Because it's usually not semiconductor. It's made of capacitors, no? When you say RAM, you follow? Okay. I'll just this. Okay. Temporary storage, which means that you know what a RAM is, no? You follow? Read write, no? Static or dynamic. We'll talk about the difference between static and dynamic, no? SRAM or DDR or SDR. Okay, do you follow? Pag static, SDR, no? Pag dynamic, DDR. Do you follow? So usually it's a cell, no? A cell is either a semiconductor or a capacitor, no? You have a control which is the control line is read or write. Okay, you have a data in. Okay, and then the select is actually a selector circuit. It's an encoder which designates an address, no? The select is actually an address. If the correct address is done, then the control which is right will be done in the cell, no? If the select address is correct, no, the control address, this is a read, no, will be written into the data out into the sense, no? Do you follow? That's a memory cell inside a ROM, no? In other, no, they will give you this is a white box, no, and then I think not later, no, the source will give you what's inside the white box. Okay, wala na. Sorry. Sorry, no, I got lost, no. Yan. Dynamic RAM, no, or static or dynamic, no. Bits are charged in capacitors. Ito yung DDR, no. Are charged in the capacitor. A capacitor is like a small battery. It can have a charge or it can lose a charge. Although charges leak, no. When you read out, the problem with a dynamic RAM is when you read from it, the previous charge is lost. So there should be a feedback refreshing of power, which means that every time you read, you have to write it also back again. It's a very simple construction, no? Because only one device is the main component here. It's called a capacitor. You know what a capacitor is, right? It's like a small battery. It stores a charge, no? It's smaller bit because capacitors can be very small, no? They can be reduced to very small sizes, no? It's less expensive, no, because it's easy to reproduce. Although they're made of semiconductors also, but they don't have a negative and positive polarities, no? They're slower. Why is it slower? Because of the required feedback power, which means that every time you read, you have to write again because it loses its previous value. So it's slower. It's usually used for main memory. That's why we call DDR, no? Dynamic RAM, no? Okay. It's analog because the range of values to store is high, no? Ibig sabihin ang kanyang 1 is a range of values from shall we say 3 to 6 volts, no? Hindi siya fixed. Okay? So the level of charge determines the value, no? Here's how a dynamic RAM structure, no? So there's a single transistor, which is the selector. Okay? When the address is correct, the selector will, rather the transistor will set on, so that this is the bit line during a write, no? Okay? During a write, no, the charge on the input, this is the bit line, will go into the capacitor. If this is a 1, this will store a value of 1. Okay? If this is 0, this will store a value of 0 because it will go back to the ground. Do you follow? So there are essentially two main components. A transistor is used for encoding or for determining the address. If the address is correct, no, the capacitor will be activated. Otherwise, it will just keep on storing the charge that was previously assigned to it. Okay? Do you follow? No? So ang gamit nito, the address line is active when during read or write when the correct address is given. The transistor switch closes when it's active, no? And it's open when it's inactive. No? During a write, a voltage in the bit line, no? This is the bit line. Do you follow? Okay. Will be either 0 or 1. So if it's 1, it will charge the capacitor. If it's 0, it will discharge the capacitor because it goes back to the ground. Then the signal address line, no, transfers the charge to the capacitor, no, because the address is active. Being active will close the transistor, no. During a read, no, the address line is selected. The charge from the capacitor goes back to the bit line. Do you follow ito? No? Do you follow? And then the charge from the capacitor via the bit line is sent back, no? Or fed back to the capacitor itself, no? Para mag-generate na naman, it will store the previous, it will not lose its previous value. Okay? Any questions so far? So the other type of RAM is static RAM, no? This is made, the main difference is a static RAM is made of transistors, no? It's not just one transistor. There's always a transistor to select the address, no? But this time, the transistors are not only used to select the address, but even to store the RAM, the value itself, no? Static RAM. Bits are stored as on or off switches. This uses, no? By the way, flip-flops. No? Flip-flops ang gamit dito. No charges to leak because there's no capacitor to charge. Now, this is faster, no, than DDR, than dynamic RAM, because there's no need to refresh, no, power when you read. Okay, during a read, there's no need to refresh power. There's a more complex construction. It's larger, no, it occupies larger space. It's more expensive. So likewise, no, there's no need to refresh. No, it's been offered twice. It's faster because there's no charging time. No, the charging will take time. This is usually used for cache. No, it's digital kasi flip-flop. Now, the DDR is used for a main memory. Do you follow? And the static RAM is used for cache. Okay, it is not used for no because it's larger and it's more expensive, no? Although it's very much faster. Okay, so ito yun, no? This uses 4 transistors, no? Do you follow? We have analyzed this before, no? You can use instead of flip-flops, no? Okay, here's the analysis. No, in a state 1, which means that it stores a value of 1. C1 is high and C2 is low. Where's C1? Ito, C1. Here's the input. Okay, the address line. This is the transistor selector, no, for the address line. When C1 is high, it will continue to be high. Do you follow? Not unless it is changed to 0. Why is that? Because if C1 is high, no, it will drive the transistor in T1. Okay, T1 will be activated, which means that this will switch on and this will switch off. Okay, when T1 activates, no, T1 activates, what happens to the ground is, okay, C1, okay, the ground becomes 1. Okay. But, okay, itong C1 na ito goes into here and this will close. This will close T4. Okay. Okay. There's a voltage here, no? When T4 is closed, where will the current go? This will close T4. So therefore, there will be no current here, but there's current into T2. So this will be 0. Okay. Okay. Ganito ang mangyari na. C1, in state 1, C1 is high, C2 is low. T1 and T4 are off, and T2 and T3 are on. Okay. T1 and T4. T1 and T4 are off. Okay. Well, let's find out why it's off. T1. Okay. T4 is off, no? Because this is 1, this is 0. Okay, do you follow? If this is 0, the voltage at 0 is, at C2 is 0. C1 is high, C2 is 0. Since C2 is 0, do you follow? Okay. T1 is off. T1 and T4 are off. That's fine. Yes, T1 and T4 are off. So off din ito. Do you follow? Okay. And T2 and T3 are on. Is that correct? Yes, T2 and T3 are on. Off ito. So these lines are cut off, no? And these lines are on. So we will continue to have a high, no? And this, since this is off, so this will be 0. Okay. And this value, no? Okay. So this voltage, T2 and these are on. Okay. Pag on ito, okay, the voltage from C1 will continue to set it as 1. Do you follow? And the off T4 will continue to set T2 at C2 as off. Do you follow? So this will sustain. This will keep on storing the value 1. Do you follow? No? Basta ang transistor is just like a Boolean value, Boolean gate. No? When it's off, it cuts off power. When it's on, it allows current. No? Pag off, no current. Pag on, there's current. In state 0, C2 is high and C1 is low. Therefore, this is C1 is low and C2 is high. Meron ba siyang diagram? Wala na, no? C2 is high and C1 is low. So this is low. So this being low, we'll set this off. Okay, and we'll set this on. This being high, we'll set this on and we'll set this off. Okay, is that correct? T2 and T3 are off. So T2 and T3 are off. This time, baligtad na, and T1 and T4 are on. Do you follow? So since T4 is on, current will not flow here, but it will flow here. Okay, and C2 will continue to be with the current, with the constant power supply. C2 will continue to be high. Okay, and this high C2 will continuously sustain T1 to be on and T3 to be off. Since T3 is off, no, the value without the no, the value on C1 will continue to be low. Off man ito, so 0 ito. Do you follow? Okay, so C1 will continue to be off and C2 will continue to be on. That's assuming that we remove all the bit lines. Okay, so it will just feedback itself, no, round and around, no. The other lines in our transistor T5 and T6 is switched, no, when the other lines are correct, no. Okay, so the value B and complement B. So this is the value B and this is the complement of B. Do you follow? So during a write, the value must be applied to B and the complement of B. And during a read, the value line is on B. During a read, okay? So saan ba yung line B? Ito, during a read, no? This, which means that this is going to be high. Okay? Kasi papunta dyan yung value ng C1. But C1 will not lose its value because there's a continuing DC voltage that will sustain it, no? That will sustain it to be high or to be low, whichever the value is. Okay? So here's a comparison. Okay? Both are volatile. No? The dynamic cell or the dynamic run as the DRAM is simpler to build because there's only one transistor and one capacitor. No? Unlike here, we have 6 transistors. Okay, do you follow? No? It's more dense because it means that it can become very small. No? There are more capacitors and transistors can be put into one small volume, one small area. This is less expensive and this needs to refresh during a read. No? This can occupy larger memory units. No? The static RAM is faster, okay, and of course it smaller size but bigger area. This is used for building cache memory. Okay. Okay. So examples are those used for library routines like the interrupt handlers, read-only memory. The interrupt handlers are stored in the ROM. Okay. And then the BIOS program, the one that is used to boot your operating system, and function tables, no? Certain function tables. So you know this already, no? Okay. Types of ROM, we have this. Ito ang pinaka-importante na. Refreshing organization, 16 MB RAM, DRAM, 4M by 4, which means that we have 4 megabyte in each bank, no? And 4 banks. Do you follow? And we have 4 banks, no? So 2048 by 2048 by 4. Okay. 2048 by 2048 is 4 gig, 4 MB, no? Kasi 2000 times 2000 is 4 million. Okay, so 4 MB. So there are 4 of this, no? So you will have an address line, okay, and the MUX will activate, no? It's a selector, multiplexer. We will activate with each bank, no? Which bank? Because there are 4 banks. And the decoder will activate the particular row in the bank. Do you follow? Okay. So now it is not indicated whether this is a non-interleaved or interleaved memory, but depending on the design, no? A typical 4M by 4, 16 MB RAM can be 4-way interleaved. Do you follow? There's a refresh circuitry that will reload the value, that will recharge the capacitors after each read. The column decoder will identify which bits, no? Because there is a 2048 by 2048 memory array, no? Okay. So ganito yung packaging. Old type ito, no? This is an 8-bit EEPROM. Okay. So we have the address lines on pins 1 to 12, no? A0 to address 20. So 1 MB ito, no? Kasi there are 20-bit addresses. 1 MB, no? Okay. 2 to the 20 is 1 MB. And D13, 14, 15, 16, and to D31. Pabalik, that's how usually an IC is numbered by pins. 1 to down, and then continue here, and then go back up. Okay. Do you follow? So pins 13, 15, 14, 15, 16, continue here. No? These are the pins that are used to store data. Do you follow? Okay. So ang addresses na pa nag-skip 1 2 3 4 5 6 7 8 9 10 10 11 then 12 13 14 15 16. I don't know why it skipped, no? But that's how the addresses when you put this on 1 MB rather 1 MB mbit, no? What ibig sabihin 1 bit lang ito. To have 1 byte, 1 MB, you will have 8 of this. Okay? A 16 mbit DRAM. Okay? This is it, no? So 16 bit mbit, no? So which means that there are 16 bits, no? For each line. So the addresses are from where you kanyang addressing, no? They follow. The VCC is the voltage. VCC is the ground. VSS is like the VCC, but it is used particularly to read back, no? Walang VSS ito. Merong VSS, no? Okay, what's VSS? It didn't indicate, no? A 256 module, no? So meron kang 5 5-bit, no? Ilang ito? Ang 512, 5. Okay. 5 of this, no? You have a memory address register which will go into the decoder, which will decode the address. Okay, and then it will give you the bits, no? Okay, the 8 bits, no, per bank. So this is a 256K module, 256K byte. Okay, bakit 256? Because there's how many? 512? 5. Kasi 5 times 5 is 25. Okay, so 5 ganito. Okay, 1 MB module organization. So that's why there are different, no? So kung 1 MB by 512, so for 256 you will have 5, no? So ilan ito? 1 2 3 4 8. You will have 8 of this, no? And 8 of this, and you will get 512 megabyte module. Okay, so ECC, no? Most RAMs now have ECC, which means that they have error correction, which means that when the value that is read is different from the actual value that is stored, it will automatically correct using the Hamming code, no? We will not discuss the Hamming code anymore, no? Okay, it's in the data structures, no? So there's an advanced DRAM, no? Since RAM, the first RAM chip, no? It's called enhanced DRAM. It contains small SRAM as well, no? It's a DRAM that has small SRAM. It holds the last line, no? The last line is usually used as the cache, no? There's also a cache DRAM. It's a larger SRAM component used as a cache or serial buffer. Pwede ba yun? Siguro in the different levels of cache, no? In the lower level, the DRAM is used, no? Because it's lower. SDRAM, no? Ito ang ibig sabihin ng SDRAM, synchronous DRAM. It's access synchronized with an external clock, which means that there can be an external clock, no? Just like an ordinary RAM, it is one of the inputs is the address. Now, SDRAM is synchronized with the CPU clock. Do you follow? Access is synchronized by an external clock, which means that it doesn't have an internal clock by itself. So since SDRAM is driven by an external clock, it can be driven along by the CPU clock. Okay. So it's synchronized with the CPU timing. CPU does not have to wait; it can do something else. So SDRAM is used to build the registers, no? Like for example, the AX register, the MAR, no? The MBR, no? So SDR, no, is used to build. Okay. DDR SDRAM sends data twice per clock cycle. Okay, so it can send 2 bytes per clock cycle. So one of the characteristics of an SDR is it can read or write in burst mode. Okay, which means that it can fire out a block in one stream. Okay, mahal ito, no? SDR. Okay. Burst mode. RAM bus used to be a very popular bus, no? Rather a type of RAM, no? Let's have a Google. It was developed by Intel. It's much faster than DDR. The main advantage of a RAM bus is it can have higher clock cycles by Intel. Ito, no? This used to be a very expensive type of RAM, no? Meron pa Kingston, no? But this was originally developed by Intel. It failed because it was very expensive, no? Hindi siya nag-sell, no? It can have very high frequencies like 480 nanoseconds access time. Okay? So, pero ngayon, during those times, it was considered fast. But nowadays, we have 2 GB, no? For an ordinary DDR. So, during those times, if you will have Mbps, or rather 8 Mbps DDR, no? A 1.6 Gbps RAM bus is very fast. Do you follow? Eh ngayon, what's the speed of a DDR? DDR4? Hanggang 2, no? 2 Gbps. Oh, 2.4 Mbps, no? Or tingnan natin na lang, no? Ito sa Crucial silang gumagawa, no? 2.4 Mbps. Ito ang speed nila, mga DDR4. 9,200 Mbps. MB, which means bytes. Okay? So 2.4 na. Okay? So if you have a DDR4 4400, you will have 4.4 Gbps. Now, during that time, a RAM bus can store 1.6 Gbps, while a DDR can only have 800 Mbps, no? So this is twice faster. Okay. It's obsolete nowadays, no? Because it was very expensive. So DDR na ang uso ngayon, no? Ano ibig sabihin ng DDR? It's a dynamic RAM. Double data rate, no? Okay. Double data rate. Dynamic RAM. Okay. SDR is synchronous dynamic synchronous RAM, no? SRAM. Okay. Any questions? We will have problems next week, okay? Next week will be probably our last week. Last week na ba tayo next week? Yes, no? I will give you sample problems na lang, no? As guide to your exams, to your final assessment. Okay? Any questions so far? No? No assignments this week? Okay? Any questions, everyone? No assignments, no exercises. I'll give them all next meeting. Okay? Any questions?
Wala, sir.
Okay.
None, sir.
So see you next week, no? It may be our last meeting. Okay? Depending on if you have questions. Bye, everyone. Thanks.
Bye, sir.
Thank you, sir. Goodbye, sir.
Sir, goodbye, sir.
Bye.